Evidence of for metal ligand covalent bonding. We explained this. We said there is a Nevel-Oxetic effect, ESR, magnetic properties, NMR, so on. So the Nevel-Oxetic effect means electron cloud expanding. Electron cloud expanding. In a metal complex, there is an evidence for sharing of electrons between metal and ligand. So the pairing energies are lowered in complexes than in gaseous ions. So because they are pairing, so they will be lowered in energy, means more stable. So indicating that inter-electronic repulsion is less in complexes and that the effective size of the metal orbitals has increased. So that's the definition of Nevel-Oxetic effect. So that effect comes from the overlap or sharing electrons between metal and ligand. So what they do if they share electrons, we say pairing will be. There will be pairing. So this pairing energy is lowered in complexes than when they were separated, or as metal ions and ligand. So indicating that there will be inter-electronic repulsion. And don't forget, the inter-electronic repulsion is what? This is from outside. This is out. This is not inter. There is intra and there is inter. So the inter-electronic repulsion is between the ligands and the and inside the complex will do what? Will increase the size of the metal orbitals. So you can see here the ligand comes with electron, the metal has or lost one electron. Will be more repulsion. So when they are a little far away, okay? And now when they combine together, when they share these two electrons, so you remember this type of sharing. I said ligands, halogen has one single electron out of 7, one single, the other pairs. What they do, the halogen will take one electron from the metal, and then when they receive this metal, will do the back bonding. The back bonding is like shared at the end of the day. They will share these two electrons. So one from the ligand and give me from the metal, we can share these two electrons. When they shared, they will be opposite in spinning and there will be less repulsion. Where before they combine, before they be shared, there will be more repulsion because they are spinning in the same phase, or let's say spinning clockwise. So they have repulsion, more repulsion. Once they shared, they will be less repulsion. So in this case, the size of the metal orbitals will be increased. So sample, define the Nevel-Oxetic effect in terms of metal ligand covalent bonding. Now, it is being found that the Nevel-Oxetic effect of ligands varies according to series independent of metal ions. So we can see these atomic number 53, 35, and you can see until the fluorine, which is 9. And this is the increase. The Nevel-Oxetic effect series for metal ions independent of ligands is following this. So without the ligand, this is the lower. With the ligand up is more Nevel-Oxetic effect. The more Nevel-Oxetic effect when the iodine is bigger than, sorry for that, the iodine is bigger than the bromine, the bigger than cyanide, bigger than chlorine, and so on until you reach to the fluorine. So see, fluorine is the smallest one. So now we are increasing the nepheloxatic effect of ligands from the lower atomic number up to higher. Or like I'm just here assigned the iodine, the bromine, the chlorine, and the halogen. Leave it for only the halogens, and you can see an increase just for halogen. Increasing the atomic number will increase the nepheloxatic effect. Where here's the metal ions, you can see manganese 4, which has more higher oxidation or more oxidation than cobalt 3, than iridium 3, iron 3, rhenium 4, molybdenum 2, cobalt 2. This is most likely equal to nickel 2, bigger than manganese 2. So in this case, higher oxidation number will increase the nepheloxatic effect, whereas the lower oxidation will be decreased. Now, if you see here, let me go out, the nepheloxatic effect being valued, and you see the table. So to estimate the reduction in electron-electron repulsion upon complex formation, in the equation below, this one, the inter-electronic repulsion in the complex is the Racah parameter B. So the B here is the Racah parameter, whereas B0 is the repulsion in the gaseous metal ion. When it is 0, it means in the gaseous, there is no ligands before the ligand. So inter-electronic repulsion, which is the value of B as an ion minus B as a complex over B was a free ion, or the gaseous. This is equals to H times K. So the H value belong to ligand, K value belong to metal ion. So every time we give such a question, we have to provide the values or this table for you to obtain the values for each part of this equation. So now, sample question, define nepheloxatic effect and write down the nepheloxatic effect trend values for 3 metal ions. You can choose any 3 metal ions, and you can choose the higher oxidation number bigger than the less one. So now the metal ion, the K value of metal ion, cobalt 3, is 0.35, whereas the ligand, like for the 6 ligand, the H 2.3. So now what you do, you just replace, if you've been given cobalt 3, 6 bromine in one complex, you can choose these 2 values, just put them here, replace H for the metal. What value for set of ligands? So there is a mistake here. Let me have a look. The metal ion K, yeah. So the metal ion K and the ligand is H. So you can just multiply 2.3 times 0.35. The number you obtain will be the inter-electronic repulsion. And here self-exercise using the data below. As I said, we have to give the table. So you count the inter-electronic repulsion from the gaseous into the complex. To complex. So now you can see this is the complex, this is the metal ion. So you can put the equation, and from the table here, it's between iron 3 and 6 fluorine. This is the iron 3, 0.24. And this is the value of fluorine or bromine, sorry, fluorine. This is the fluorine, 0.8. So 0.8 times 0.24, and the value will be 0.192. What is it? It is the inter-electronic repulsion. So here everything is being written, and can show you. Therefore, the reduction, and then you can mention this, the reduction in inter-electronic repulsion going from gaseous to will be about 19%. So once you get the value here, you can mention that the reduction in the inter-electron repulsion from gaseous to complex will be about 19%. And here are the sample questions. So electron spin ESR. And this picture was from my lab. I took this picture. And now you can see electron paramagnetic resonance, EPR. And there is a ESR, electron spin resonance as well. So these machines are used to measure the EPR and ESR, electron paramagnetic resonance, EPR, or electron spin resonance. So this type of spectroscopy is a technique studying materials with unpaired electrons. So the basic concepts of EPR are analogous to those of nuclear magnetic resonance, NMR. But it's the electron spins that are excited instead of the spins of atomic nuclei. So it will be the what? The electron spin instead of the atomic nuclei. NMR is the nuclear, atomic nuclear. Unpaired electrons, single electrons, behave as magnets and align themselves parallel, lower energy, or anti-parallel, higher energy to a magnet field. You remember these are paramagnetic, so they will attracted to the magnetic field, and these are the diamagnetic, which is they repelled, they go outside the magnetic field. We call it the alternative magnetic field. So they have magnetic fields for itself, for each one of them. But when they put in an alternative magnetic field, so they will be either attracted or repelled. So in this case can be observed by applying radio frequency radiation. Okay. Now, this is when the metal ion here, we have the ESR. So we wanted to mention there will be unpaired electron linked to a ligand containing nuclei with a spin quantum number not equal to 0, hyperfine splitting. ESR signal is observed in the covalent bonding between metal and ligand. So ESR for this spectrum, for this complex, paramagnetic low spin, D5. Paramagnetic low spin. Sorry, this is the low spin. This is the high spin. So is recorded for the solid solution. In this case, diamagnetic spin. Low spin. So this is the low spin D6, and this is D5, this is the D6. Low spin, low spin. Okay, so we can differentiate between the low spin using this ESR signals. And we can assign what is the difference between them, and there will be term symbols going up. So explain ESR as evidence for metal ligand covalent bonding. So you can mention that the ESR is very good to use the electron spin resonance to know what type of magnetic field or behavioral properties of the complex. Magnetism. Now we come to explain the magnetism is a class of physical phenomena that includes forces exerted by magnets on other magnets. It has its origin in electric currents and the fundamental magnetic moments of elementary particles. These gives rise to magnetic field that acts on other currents and moments. All materials are influenced to some extent by magnetic field. The strongest effect is on permanent magnets, which have persistent magnetic moments caused by ferromagnetism. This is the strongest effect. Okay. So anyway, so we have here most materials do not have permanent moment. I just want to bring this down. I wanted to apply play. Oh my God. So that's not going away. Okay, wait. So I can do this. Yeah, it's gone. So now we have the most materials do not have permanent moment, so they are paramagnetism. If some are attracted to the magnetic field is paramagnetism, other are repulsed or repelled will be diamagnetism. Other have much more complex relationship with the applied magnetic field, spinning glass behavior, and antiferromagnetism. So substances that are negligibly affected by magnetic fields are known as non-magnetic substances, including copper, aluminum, and plastic. So they are negligibly affected by magnetic field. Non-magnetic. So we have either attracted to the outer magnetic field or repelled, or they don't do anything like plastic, which are non-magnetic. You can see here magnetic state or phase materials depends on the temperature, pressure, and the applied magnetic field. So we have three things affect the magnetic state: temperature, pressure, and the outer magnetic field. Material exhibits more than one form of magnetism depending on its temperature, etc. So here you have Michael Faraday, who studied the magnetism, and here you can see a magnet made of Linico iron alloy. This is a magnetic quadrupole. You can see north, south, or so see the northeast with the southeast. So they are quadrupole or pole, quadrupole. And here you can see the outer. So these are the plus minus, and here the dipole, electromagnetism. Magnetic properties, or we call it susceptibility, magnetic effect, a mu effect. And we studied this before. I remember we talked about this, but here we just want to mention maybe something extra. So here, yeah, we can mention we talked about the mu spin only will be 2 under square root s plus 1 when you talk about the spin. If you talk about the number of electrons, number of unpaired electrons, you use this equation, which is again a mu spin only. So either you use the spin or you use how many single electrons. So this will do the theoretical magnetic moment. We call it mu effect. And this would be the maybe practical. So now we said the effective magnetic moment measured experimentally by molar magnetic susceptibility. We call it XM. So this is practically XM and expressed by Bohr magnetons, MUB, where 1 Bohr magneton equals to 9.2 times 10 to the power minus 24. So where is this line came from? Came from here. Okay, so now what you have is the mu effect. This is the theoretical, practical magnetic moment. So J and time and T, temperature in Kelvin. So this is 9.27 times 10 to the power minus 24 joule per time. Sorry, per temperature. The temperature in Kelvin, but the practical magnetic moment is being measured by 2.828 times the square root of XM. What is the XM? We said now is the magnetic susceptibility, the experimental. This is times the temperature. So we use the Gouy balance or Faraday or Sequid to measure the XM, this one, for each complex, which makes us use of interaction between unpaired electrons and magnetic field. Paramagnetic is attracted to the applied field, whereas diamagnetic is repelled into it. Paramagnetic sample drawn into magnetic field by the amount that depends on number of unpaired electrons. So change in weight from movement of the sample is recorded. So the Gouy balance will measure the weight changing in the sample. So there is a weight change when attracted or repelled. And then using the equation to obtain magnetic moment mu effect. So I think we have applications for such magnetic susceptibility. So spin only values magnetic moment mu effect for high spin complexes, first row D block. You can see a metal ion is scandium 3, which is D0. Titanium 4 is a D0. When D0 mean no spin, nothing, 0, 0, 0. Titanium 3 left with 1 electron. This 1 electron has a spin of half. So when you apply how many single electrons? 1 times 1 plus 2 under the square root will remain 1.73. You remember these before, the values, but now we're just showing how these values comes out by this equation. If you have 2 electrons, the spin half and half would be 1. So we have 2 electrons, 2 times 2 plus 2 will be under the square root 8, and then the 8 is 2.83. So on, you come back to the 0, and you can see our value is 1.73, 1.73, 2.8, 2.1, and so on. The maximum one is 5 electrons, and here you have 5.92. So now, observed value by practical, experimental. This is theoretical, and this is experimental. Mu effect over mu Bohr or Bohr magneton. So we found it is somehow very close to the theoretical measures. Sample questions at room temperature. Observed mu effect for this complex was 4.75. Bohr magneton. Is the complex high or low spin? So when you have 4 single electrons, you remember we talked about this. When you see 4.7, it means about 4 electrons. So 4 single electrons, you should arrange them in 4. If you arrange them in low spin, this is a high spin. If you arrange in low spin, you end up with the value of 2 point something. So here, if you have 4, you can say it's a high spin, depend on 4 electrons. Chromium oxidation, D4. Similarly, you can bring this and you can measure 4 plus 2 will be 6 and 24, and you end up with a value. This is it, 24. So 24 under the square root will be what? Will be 4 point something. So 4.9 is for what? For 4 electrons. So now I want to arrange these under the square root, and everything is not properly put. I put this here. Oh my God. Anyway, this is the square roots. These lines are for the square roots. So everything is measured theoretically. This is the theoretical, and this is the practical. And you for high spin mu, this is the theoretical, 4.9, close to the observed value, and consistent with the high spin. Curie temperature. As the temperature increase, we said there are many terms affect the magnetic property is the temperature. One of them, very important. Thermal motion, entropy competes with the ferromagnetic tendency for dipoles to align. When the temperature rises beyond the certain point, the called Curie temperature. So there is a second order phase transitions, and the system can no longer maintain the spontaneous magnetization, although it still responds paramagnetically to an external field, but it will be less. So below temperature, spontaneous symmetry breaking the magnetic moments become aligned with their neighbors. And the Curie temperature of itself, critical point, and magnetic. So everything is being measured. You can see effect of temperature. You can see increasing the KT per lambda and an increase of mu effect over Bohr magnitude, and you can see magnetization as function of the external field described by the high traces curve. So you can see the curve with these, so increasing from osmium 4, ruthenium 4, manganese 3, chromium 2. So Kotani plot for T2G4 as 4 points valued of mu effect. 298 Kelvin indicate temperature has no effect on first row manganese and chromate. So increasing temperature has no effect on manganese and chromate. Temperature has effect on second row ruthenium 4 and third row osmium 4. So self-exercise or simile knowledge, you can exercise these questions, and we talked about the magnetism, and you can find the theoretical value compared to the given value, the practical, and see which one will apply the electron to be high spin, low spin, and the calculation of number of electrons depend on these. If you've been given the 2.8, what does it mean? 2 single electrons. When if you've been given 4 point something, it will be 4 single electrons. We have more explanation and more calculate the theoretical value of magnetic moment. Deduce number of ampere electrons in the complex. Is it the complex high spin or low spin? This is very common. And as you see here again, because I changed the computer, so the PowerPoint is not giving me the same designs I made on another computer. So everything here is what in under the square roots. Okay, doc. So these lines belong to the square roots. Ferromagnetism, anti and ferromagnetism, anti-magnetism, and ferrimagnetism. So now what do you have here? Metal centers, these are without magnetism. These are the oxide metal centers, oxides, chloride, metal surface showing magnetic domains. If they are arranged parallel or anti-parallel or something, so we can see from the shape are these ions in the same direction, different, which direction? So paramagnetism, single electrons, different direction, spin. So you can see diluted magnetism, magnetic center separated from each other by diamagnetic species. So metal centers have no interaction with each other. Diluted magnetism. Paramagnetic center separated from each other by diamagnetic species. When paramagnetic species very close together as in bulk metal or separated by species can transmit magnetic interactions like oxides and halides, the metal centers may interact or couple with one another. This interaction may give ferro or anti-ferromagnetism. Ferromagnetism, large domains of magnetic dipoles. This is the highest magnetism, is the ferro, aligned in the same direction or parallel. So neighboring magnetic dipoles are aligned on the opposite direction. Ferromagnetism leads to increased paramagnetism as in iron. So iron at temperature up to Curie temperature of 1000 Kelvin, which prevails normal paramagnetic behavior. Antiferromagnetism occurs on cooling. So how can you make the antiferro? You can cool the sample below Néel temperature, Tn. So the temperature decrease, less thermal, found in the oxide, in the manganese oxide, nickel oxide, hematite, chromium metal alloys, and some organic molecules. So opposite, anti-parallel, we can find it like this. These are ferromagnetics. This is the anti-ferro. Ferrimagnetism, materials in which the magnetic moments of the atoms are different on different sublattices are opposed. Antiferromagnetism, however, in ferrimagnetic materials, the opposing moments are unequal. So you can see the ferrimagnetism. So in the ferromagnetism, they are equally opposed, but here is partially opposed. Where can we find this ferrimagnetism? In different, in the complex where there is a different oxidation number of the same atoms, atom centers. So we have one complex, one of them, part of it is with iron 2, another part is iron 3. So here, when they aligned opposite to each other, ferromagnetism, but partially unequally. So we can see here, these we have the iron, and you can see there is a bridging between them. So can exchange low to high spin, or vice versa on change in temperature and pressure. We call this spin crossover. So there will be a spin crossover. This is a field of science in chemistry, very, very interesting, and more applications in the medicine, and they can use the spin crossover. So when you have two metals in different oxidation states, like nickel 2, iron 2, super exchange will be, or you have iron 2, iron 3. You can see this is metal center. This is another metal center. Between them, nickel. So the nickel is a bridging between these two, and here will be super exchange of magnetism. So a table of ferromagnetic materials, you can see Curie temperature. This is the highest temperature can bear by this complex, and then they lose the magnetism. And these are the Curie temperature as well for different samples. Higher than nickel metal. So cobalt has Curie temperature, cobalt 1388, whereas the nickel has 600, almost double. Summary knowledge, you can explain or define the ferromagnetism and ferri and anti-ferro. And here we have Heusler alloys, where there will be non-magnetic alloys, stainless steel, with a minimum of 10% chromium and composed of no ferromagnetic materials. And ferrimagnetics exhibit by ferrites and magnetic garnets, Yttrium iron garnets, the oldest known magnetic substance, magnetite, iron 2, iron 3 oxide, all of these are applications. And here we can see the north-south dipole moments and how in the alignment of the atoms in the magnetic field without, and here there is an inducing magnetic field, and you can see the energy increase, so you can lose magnetic, when there's a Bohr magnetism. So here we have the nuclear NMR spectroscopy, very important to analyze the sample. And these samples, basically another form of absorption spectroscopy, akin to IR, UV, used to identify compounds. We need to identify compounds, we can use NMR. We have worked on radar frequency as well, lead them to study NMR. So a nucleic magnetic resonance, NMR, is a property that magnetic nuclei placed in a magnetic field and applied electromagnetic EM pulse, which causes the nuclei to absorb this energy pulse and radiate it back out. So this is how the NMR worked or works. So different atomic nuclei within a molecule resonate at different radio frequencies for the same magnetic field strength. The observation of such magnetic resonance frequency of the nuclei present in a molecule allows any trained user to discover essential chemical structural information about the molecule. Of course, I remember we were preparing a sample or the new chemicals, and these chemicals should be examined or identified, its functional groups, everything, data collected by, I remember once I make crystals, I send them to the microanalysis to identify carbon, nitrogen, oxygen, halogens presence. And then I send a sample, or I crush sample to do the IR to assign the peaks every which functional groups I have. Then UV, if it is attracted to UV, or how can I find functional group using UV-Vis spectrum machines, and then we send magnetic property to have the data to assign it. Is it paramagnetic, is diamagnetic, and then to check the crystal structure of it as a final approach, maybe to identify the molecule. So using the X-ray spectroscopy, and then NMR, and all these techniques used to put a full data for the sample, for the molecule, for publishing. So any published paper, don't accept unless there is a reason. So you have to make a full tests for the sample and make 100% sure of what's the structure of this chemical, the new chemical. And we publish papers depend on these tests. So we learned a lot during our PhD research course, and we used all the techniques, which is now, when I explain them, I remember my days during these PhD years, how I was close to the machine. I saw different machines to have different datas to end up with the final decision about the exact structure of this new molecule, which should be pure. Purity is important. So this is the sample. You put it in the magnetic field, radio frequency oscillator, and then you go to the amplifier. Then there is a chart on a computer, and you can assign these peaks belong to which groups. And NMR, I remember we were assigning the like hydrogen NMR. There is a carbon NMR. So you just count or depend on how many hydrogen you have in the sample. This is how you apply radiation from here, electromagnetic radiation, EM, hit the sample. So this will, the nuclei will be excited, absorb the energy. Some of them will be excited and lose the energy for reflected radiation. And you can hit the electrons or you can hit the nuclei. And this is the magnetic field, the external magnetic field, south and north. And you can see these atoms or electrons will be excited, absorbing energy and give reflected radiation, which this will be recorded on a computer, and to find exactly every peak related to which excitation. So this, like we call it, proton 1 or phosphor 31 could absorb radio frequency energy. And we have every data here as well, how you apply. This is the molecule, and there will be dipole if there is a single electrons. And when you apply the energy from external magnetic field, and what will happen? So these are one of our, this is the benzene ring. Here is the acetylene. You can see the alignment. And these are the I think one of our samples. There's a cobalt, there's a nickel, applied field, HO. And then you have every group on the NMR spectrum from 0 to 12. Every group, once we see the peak, we know this is belong to this proton hydrogen related to alkyl or to double bond near aryl, or triple bond, this hydrogen related to acetylene, related to carbonyl. Every area in the spectrum, you can assign a peak, and you know if like you found them in the ppm between 5 and 6, there will be these kind of functional groups. If you find it only the proton for the benzene ring, it will come as a peak on the number 8 ppm, and so on. Aldehyde, ketone, whatever you have, everything is on chart, and you can see proton chemical shifts. And here how the chart comes out, and you can see the peak. And this peak has a height. Every peak has a height. It's being counted, calculated, and we can find how many protons here. Is it 9 protons, 3 protons, 4? So every peak has a height. This is being given by the computer, these numbers, and we can measure and identify the functional group on the spectrum of NMR. This is one of my new structures. We assign the hydrogen proton NMR, and we found every group exactly in its position, identical to the structure. This is X-ray structure in UCD, University College Dublin. And here what we have, CMR spectra, carbon, and you have here the similarly, and carbon 13, always like a noise, but the proton NMR is clear, good. This is one of our structure from Dr. Azad Mahdi, database discover molecules, which is dicobalt. hydroxamic acids. So now I stop here and then talk about coordination complexes in the living systems, which is very important.